So in our previous video, we built up this beautiful table that summarizes and organizes clearly a whole bunch of concepts that we've explored separately, and we're going to put them all together. We've talked about bases in nucleophiles, we've talked about substitution and the leaving group, and now we built up in that previous video how those come together to create or to determine specific mechanisms. So I strongly encourage you to go back and visit that other video if you haven't, to understand where this table is coming from. From now on, we're going to just use this table. So we won't go back and explain it every time we use it. From now on, we're just going to use it. But there is that separate video that explains the whole concept behind it. All right, well, let's say, in this case, instead of just talking generally and conceptually like we did last time, we are being given specific molecules. So first we're given 1-bromobutane. Bute, that means we have 4 carbons, AN, all single bonds, E, it's a hydrocarbon. So 1, 2, 3, 4. Now I can number this however I want. I'm going to number it from left to right. On carbon number 1 we have a branch. The branch is a bromine. So this is 1-bromobutane. Okay, now, that's our substrate. And the crucial thing to recognize there is that the leaving group is on a primary carbon. This carbon is only bonded to one other carbon. It's a primary carbon. So the leaving group is on a primary carbon, and what that means is that when we're trying to think of the mechanism, only the mechanisms in that first row will be relevant. Now, which exact mechanism happens, that's what they're asking us for. They say, identify the mechanism or mechanisms expected to operate when you treat 1-bromobutane, leaving group on a primary carbon, with the following reagents. So in this first one, we have sodium hydroxide. And you would recognize that sodium hydroxide is a strong base and a strong nucleophile, which means that we will have, where these two overlap, we'll have 2 mechanisms. We'll have the E2 mechanism, that'll give us the minor product, and we will also have the SN2 mechanism, which will give us our major product. Now this exercise is not asking us to draw those products, it's just asking us to recognize the mechanism. We're slowly building our way up toward drawing them. Okay, so then if we go to this next one, in this whole exercise we're always dealing with 1-bromobutane, and so we will always be dealing with this first row in this exercise. So here we have NaSH, and you'd recognize that NaSH is a weak base and a strong nucleophile. So the overlap between the column and the row gives us only an SN2 mechanism. So the product you'd expect would only be the SN2 product. For C, we have TBUOK, potassium tert butoxide. Now the tert butyl group is really a carbon chain. And so that is really like this R. It's bonded to an oxygen and then to an ion, so that's a strong base and a strong nucleophile. So in this case, the potassium tert butoxide would give us 2 products. We would have an E2 product, and that would be our minor product, and we'd also have an SN2 product, and that would be our major product. Then we have sodium methoxide. Sodium methoxide is one of our strong bases and strong nucleophiles. Because we're dealing with 1-bromobutane, we saw that the leaving group there was on this primary carbon. And so again, we get an E2 mechanism that gave us our minor product, and the SN2 mechanism will give us our major product. So you could see how we could combine our recognition of bases and nucleophiles with our recognition of what type of carbon the leaving group is on, and we can use that to very quickly see what type of mechanism the reaction is going to happen by. And once we know that, we can start to think about drawing our product.